Hello everybody. In this video, I want to go through a few examples of the types of problems we're going to see on our homework dealing with the gas laws and the ideal gas laws. The first one is just going to be about converting between the various different units of pressure that we have. And it says the barometric pressure in Flint, Michigan one Sunday afternoon is 100.7 kilopascals. So the barometric pressure is the pressure measured using a barometer. This is the pressure of the air at any given time. And we pay attention to this because it's important for the weather and predicting the weather. What is this pressure in pascals, bars, and what is it in ATMs, atmospheres, millimeters of mercury, and torr? So the first thing we need to do whenever we're doing our conversions is just come up with a bunch of facts. And you could string a lot of different ones together here, but the ones that we're going to use right now is that 1 bar is equal to 0.9869 atmospheres, which is 100 kilopascals, which is 750.062 millimeters of mercury, and it's the exact same amount in torr because millimeters of mercury and torr are the same unit, which is different names given to them. So the first thing we need to do is start off, we'll figure out how many pascals this is. So we have 100.7 kilopascals. This is just a simple conversion within a metric system, right? So there's 1,000 pascals in every 1 kilopascal. So this is 100,700 pascals. Next, we'll convert this to bars. So up here, we see that for every 100 kilopascals, that's 1 bar. We say that we have 100.7 kilopascals. We set up our conversion factor to cancel the kilopascals. And we see that is 1.007 bar. Next, we need to convert to atmospheres. We could have just started back over with 100.7 kilopascals and said there's 100 kilopascals for every 0.9869 atmospheres. But I actually chose to take the output of this one, 1.07 bar, and use this other conversion factor here, saying that there's 0.9869 atmospheres for every 1 bar, and I get that that is 0.9938 atmospheres. We do something similar here to calculate the millimeters of mercury, and then we recognize that millimeters of mercury, there's 1 torr for every 1 millimeter mercury. So we get the same number of torrs as millimeters of mercury. Next, we'll take a look at a Boyle's law problem. In this example, we have a 378.3 millimeter cylinder inside an internal combustion engine. It contains a gaseous fuel-air mixture that approximates an ideal gas. A piston compresses this gas to 211.9 millimeters before ignition. What is the final pressure of the gas given that the initial pressure was 1.10 atmospheres? So if we draw out a little diagram of what's happening here, we have a cylinder. It initially contains gas at 1.1 atmospheres. It has a volume underneath this piston of 378 millimeters. We push down on the piston that compresses the gas, making the pressure in here raise and go higher, right? And the final volume it has is 211.9 millimeters. Boyle's law states that the pressure initial that we have here are 1.1 atmospheres times the volume that we initially had is going to equal the final pressure that's in here, the thing that we want to know, and times the volume that it winds up at. If we rearrange this for the pressure, the unknown variable, we get this equation right here. And that's just basically by dividing over by V2 and kind of factoring some stuff out and rearranging some stuff, we get that. Once we plug in our values, we get 1.10 atmospheres. And then we have 378.3 milliliters on top, and we have 211.9 milliliters on the bottom. So a couple of important things here. I've chosen to write this way because we can pretty clearly see here that these units are going to cancel. And those units canceling are the reason why we didn't have to do any conversions here. We need to match up these two units in order to get a dimensionless quantity, and we're going to get out atmospheres out of this, which is the pressure unit that we want. Also, you'll notice that the higher, larger volume is on top, the lower one is on the bottom. That means that this whole ratio here is going to be greater than 1, and it's going, when we multiply it by the initial pressure, it's going to make it larger, which is what we need, because we know that this is a compression and this is going to be larger. We're going to have more pressure in there. So those are your little sanity checks when you're going through one of these. If we do all this math out, we get 1.96 atmospheres before ignition in the cylinder. So next, let's take a look at a Charles law problem. A party balloon contains 1.783 liters of helium at 23.6 degrees Celsius. When the balloon is placed in a freezer, the temperature of the gas is decreased to -8 degrees Celsius. What is the new volume of the gas? So we start off with our balloon. It has a volume of 1.783 liters. It's at 23.6 degrees Celsius, roughly room temperature. We put it in the freezer. It contracts down. It's going to get smaller, right? Because all of those molecules in there are going to start to compress and get closer and closer together, filling up less volume. And it's going to have a final temperature of -8 degrees Celsius. So the first thing that's very important whenever you're doing one of these problems, that you can never have Celsius or Fahrenheit or any other unit other than Kelvin. So we first need to convert this initial temperature and this final temperature to Kelvin. The way we do that when we're converting from Celsius to Kelvin is we add 273.15. When we do that, we get our initial temperature here is 296.8 Kelvin, and over here is 265.2 Kelvin. Then we look at Charles' law. Here we have that the volume initial divided by the temperature initial is equal to the volume final minus the temperature final. We want to know the final volume. And so when we rearrange to solve for that, we get that it is equal to the initial volume times the final temperature divided by the initial temperature. We go ahead and plug those values in. We see that these both cancel, and we're not getting any negatives here, right? Because we would have gotten a negative here if we had not converted to Kelvin. And then we get out, finally, 1.593 liters, which means that the balloon did contract a little bit. It's a little bit lower now than it was initially. So all of our sanity checks work out. All right, now let's look at a Gay-Lussac's law problem. And in this example, a can of hairspray contains gas at 7.83 bar and 24.3 degrees Celsius. When left in the hot sun, the can is heated to 34.6 degrees Celsius. The maximum pressure the can can hold is 11 bar. Question is, does the can explode? So we have a fixed volume system here. The can isn't going to get any bigger or any smaller. And we're going to have 7.83 bar initially at 24.3 degrees Celsius. It starts heating to 34.6, and the question is, what is the pressure inside this can now? First thing we need to do is convert these temperatures to Kelvin. So we can see that 24.3 is 297.5 Kelvin here. And over here, we're going to be at 307.8 Kelvin. We take a look at the Gay-Lussac's law. We have the pressure initial minus the temperature initial, the pressure final minus the temperature final. We solve for the final pressure, and we get an equation that looks like this. We plug in the initial pressure. We have our temperatures here. Again, we have the higher one up here because as we heat this, we're going to be adding energy to the molecules. They're going to collide with the inside of this wall more than they were before. It's going to cause the pressure to go up. We see that these units cancel. And when we do the math out, we get 8.10 bar. That 8.10 bar is less than the 11 bar that the can hold, so the can does not explode. Let's take a look at an Avogadro's law problem. In this example, a nitrogen tank holds 36 liters at STP, that stands for standard temperature and pressure. How many moles of gas does the tank contain? So we need a couple of facts here before we are able to tackle this problem. It doesn't seem like we have enough information yet. First, we have the STP is 273.15 Kelvin, so 0 degrees Celsius, and 1 atmosphere. The second fact is that a mole of ideal gas occupies 22 liters at STP. And so we have this conversion factor here that when we're talking at STP and only at STP, we can say that there's 22 liters of gas for every 1 mole. With this fact known, we can convert the 36 liters of gas to moles by dividing by 22 liters. We get multiplied by 1 mole, and we see that that tank is holding 1.6 mole. We can combine these sorts of problems with any of the other mole type problems that we've asked before. In this question, we're asking, what is the mass of 100 liters of argon at STP? So if we have 100 liters, we divide that by 22 liters for every 1 mole here, and we get 4.5455 moles is in that 100 liters. Do recognize that when we're making the approximation of a gas as an ideal gas, it doesn't matter which one we had, whether it's argon here or nitrogen up there, we're still going to say it has 22 liters for every 1 mole. What does matter now, though, is that we have argon, and we're going to have to go to the periodic table and look up its atomic mass, because this is one of those noble gases. And we're going to say that we have 4.5455 mole, that there's 39.948 grams for every 1 mole, and so this is 181.58 grams of argon that is contained in this 100 liters. So far, all of the other laws that we've looked at, we're always going to have one of these variables here. The pressure, volume, and temperature is fixed. It is important to realize that pressure, volume, and temperature are the values that are needed in order to define any gas, whether you're calling it an ideal gas or not. But if we fix one of them, we wind up getting one of the other laws that we've used so far. But sometimes they're all changing at once, right? Sometimes you don't have a can that has a fixed volume, or you don't have the pressure remaining the same before and afterwards. Sometimes the temperature does change during a process. And in a situation like that, we need to bring in the ideal gas law where we have all of the variables present here. And it's usually written like this, but we can rewrite it to solve for any one of the variables. And the most interesting one is probably this first one, because what we basically did is we found that when a gas was behaving ideally, which we talked about is when it's dilute, high temperature, relatively high temperature gas, if we take the pressure times the volume and we divide it by the number of moles and the temperature, this always comes out to the same constant, this R constant. And the R has different values depending on which units we use here. So you need to match your R constant, the gas law constant, to the units that you are working with. But you're going to see in our homework, we're pretty much just using one R constant. But you can always look it up. There's many different numerical values that are all corresponding to this same number. We can solve for temperature, number of moles, we can solve for pressure, we can solve for volume, and we'll get all of these different things. And we'll always be able to see that, for instance, pressure and temperature here, when the temperature goes up, this whole value goes up and the pressure goes up. So these are directly proportional. Whereas the pressure and the volume here, when the volume goes up, this whole value goes down and the pressure goes down. This is what's known as indirectly proportional. Let's take a look at an ideal gas law problem. A 23.82 gram sample of gaseous oxygen is held in a 300-liter tank at 24.73 degrees Celsius. What is the pressure inside of the tank? So here we're given a temperature, we're given mass, so we weren't even given our moles directly. We're going to have to figure out the moles here, and we're given a volume. And we're going to have an equation that relates the volume, temperature, and amount of the sample together. So the first thing we're going to do is we're going to figure out how many moles of oxygen is that. So we have 23.82 grams. We know that oxygen is a diatomic, so we need to have double its atomic mass here. So that's 31.998 grams. And this is 0.7444 moles of oxygen. It's important to note that when you're dealing with molecules, you do need to use their formula mass here. Okay. You would not use, say, just the atomic mass of oxygen, because it is the O2 molecule that is moving around and participating as a gas. It needs to stay together, and we're going to use the formula mass. Next, again, we always need to be using Kelvin for all of our units here. So we're going to take the 24.73 degrees Celsius. We're going to add our 273.15 and we get 297.88 Kelvin. So now we have our useful units to us. We're in moles, we're in Kelvin, and we start plugging it into our ideal gas law. So we're going to have N times R times T divided by V. And so we have the moles. First, we have our R value, and you notice that we're going to use this value 0.08206 liters times atmospheres divided by moles Kelvin. So we already have our moles canceling here. And then we have our temperature of 297.8 Kelvin. We get our units of Kelvin canceling. And then we're going to divide it by the size of our container, 300 liters. And that's going to cancel with this liter up here. And we wind up winding with the units of atmospheres. So when I multiply these together and divide by 300, I get 0.06065 atmospheres inside of the container, which is like a vacuum. right? This is less than 1 atmosphere, so they would be like emptying this tank, sucking the oxygen out of it, and creating a vacuum in this case. Now I'd like to take a look at an example of a Dalton's law problem, where we're going to have that the partial pressure, the pressure due to any one component in a mixture of gases, is equal to the mole fraction of that component times the total pressure. So let's go through this problem here. A 200-liter tank at 26.78 degrees Celsius contains 8 moles of methane, 26 moles of argon, and 2 moles of H2. What is the partial pressure of the methane in the tank? So the first thing is that we need to know the total pressure inside of the tank, and we weren't given that. So the first thing we're going to do is we're going to go ahead and calculate the total pressure using the ideal gas law. And you're often going to see these kind of like Dalton problems combined with an ideal gas law problem. So to find the total pressure, we first need to know the total number of moles. So we have 8 moles of methane, 26 moles of argon, and 2 moles of hydrogen. Altogether, we have 36 moles in this container. The temperature, again, was not conveniently given to us in Kelvin, so we're going to have to convert that temperature to Kelvin. By adding 273.15, we get that the temperature inside the container is 299.93 Kelvin. And then we go and plug all that into our ideal gas law equation, the same one that we just used. We have the number of moles, 36 moles. We have our R value. We have our temperature, and we have our volume down here. We'll go through and make sure that we're canceling all these units, because that's how we check to make sure we got them all right. And we did, and we see that that's 4.430 atmospheres. So that's the total pressure inside the tank. But we were asked what is the pressure of just the methane. And to know that, we're first going to need to know what is the mole fraction of methane. We know that the mole fraction will be the number of moles of methane divided by the total number of moles. We already calculated the total number of moles. We know that there's 36. We know that 8 of those moles are methane. So we take 8 divided by 36, and we can see that our mole fraction is a dimensionless quantity where we cancel these units, and it's 0.22. Little sanity check here. 0.22 is between 0 and 1. It is in fact a fraction, so that does make sense. Now we get into our Dalton's law problem here, where what we're going to say is that the partial pressure due to methane is equal to the mole fraction of methane times the total pressure. The mole fraction is 0.22, and the total pressure is 4.430 atmosphere, the same one that we just calculated here. We do this multiplication, and we see that the methane is 0.97 atmospheres, which is a value less than the total pressure. So some portion of this is due to methane. It's 0.97 atmospheres of it, and that all makes sense.